welcome back. In this video, we're going to be looking at graphing exponential equations. Exponential equations that we graph are written in the form y equals a times b to the x minus h plus k, where a, h, and k are the transformations on our function to the parent function y equals b to the x, as they have been all year. A will be a vertical stretch or shrink. It's also going to be a reflection over the x-axis if it's negative. H will be a horizontal shift right or left. So x minus 4 would be a shift right 4. K is a vertical shift up or down. So a positive K would shift our graph up, and a negative K will shift our graph down. We have a couple key things that we want to remember when we're graphing. That is b to the 1 is equal to b to the 0 is equal to 1, and b to the negative 1 is equal to 1 over b. So we're going to keep all of this information in mind over here as we get an example problem up. The example we're going to look at is graphing the equation k of x is equal to 4 times 5 halves raised to the x plus 2 minus 6. The first thing we want to do is think about what do exponential functions look like. Exponential functions have a horizontal asymptote. I want to look at what my value of b is. B is bigger than 1, so this is going to be a growth equation. So because it's a growth equation and a is positive, I know that my graph is going to look something like this. So now I have an idea of what I'm expecting my graph to look like, and I can move on from there. I first want to start with the asymptote of my graph, and the asymptote of exponential graphs will always be y is equal to some value. In the case of this problem, or in the case of all exponentials, y will always be equal to k as our asymptote. K in this problem is negative 6, so y is equal to negative 6 is my asymptote. So 1, 2, 3, 4, 5, 6. I am going to graph that asymptote as a dashed line, and I will label it y is equal to negative 6. So I'm now expecting this shape on here. Okay, the next thing I want to do is make a table of values that includes 3 points. In my table of values, I want to pick values of x that will be convenient. Convenient values of x mean I'm going to try to make my exponent. I'm going to try to make my exponent negative 1, 0, and 1. So I want the exponent to be negative 1, 0, and 1. Those are just good values to use. I'm going to start with those. If those don't give me things that look good on my graph, then I'll move on from there. But I really don't want to deal with 5 halves squared or 5 halves to the 5th. Things like that, if I've got 5 halves cubed, I'm getting into numbers that are going to start to be a little bit weird, especially if we get up to really high exponents here. So I like to work with exponents that are kind of reasonable. So to make my exponent negative 1, I'm going to be solving this equation. Negative 1 is equal to x plus 2. So that means that x should be equal to negative 3. To find out what y should be, I'm going to go through the math. So that's 4 times 5 halves raised to the negative 3 plus 2 minus 6, or 4 times 5 halves raised to the negative 1 minus 6. 5 halves raised to the negative 1, we flip that. So that is 4 times 2 fifths minus 6. 4 times 2 fifths is going to be 8 fifths. 8 fifths minus 6. 8 fifths is 1 3/5, or 8 fifths. If I pull out a calculator, 8 divided by 5 is 1.6 minus 6 is going to give me negative 4.4. So this is 1.6 minus 6, negative 4.4. So I now have the ordered pair negative 3, negative 4.4. 1, 2, 3, 4.4. Negative 3, negative 4.4. All right, to make my exponent 0, x should be negative 2. So that's going to give me 4 times 5 halves raised to the negative 2 plus 2 minus 6 is equal to 4 to the 5 halves raised to the 0 minus 6. Anything raised to the 0 is 1, so this is 4 times 1 minus 6, which is just 4 minus 6, or negative 2. So I have the point negative 2, negative 2. And if I plug in 1, or if I want my exponent to be 1, that means I should input an x value of negative 1. So that would give me 4 times 5 halves to the negative 1 plus 2 minus 6. 4 to the 5 halves, or 4 times 5 halves to the 1 minus 6 is just 4 times 5 halves minus 6. 4 times 5 halves will end up being 10. Minus 6 is going to be 4. So then I have negative 1, 1, 2, 3, 4. These 3 points, I'm not quite getting a great shape, so I might actually try to see what happens if I use negative 4 as an exponent. Because I think my graph should kind of curve down, but I'm not really getting that flattening out curve. You could just sketch it in, or you can check another point. So that is 4 times 5 halves to the negative 4 minus 2, or to the negative 4 plus 2 minus 6 is equal to 4 times 5 halves raised to the negative 2 minus 6, or 4 times 5 halves, or I'm sorry, 4 times 2/5 squared minus 6. So that is 4 times 4 over 25 minus 6. So on my calculator, 16 divided by 25 is 0.64, minus 6 is going to give me negative 5.36. So if I go to negative 4, 1, 2, 3, 4, negative 5.36, I can now kind of see the curve. My graph is going to look like that, approaching the asymptote here. When I look at my graph, I can see that this line will approach this asymptote but never reach it, and all of my values are above it. The domain for all exponential functions is all real numbers. And the range, because my graph is all above this, will be y is greater than negative 6. If a had been a negative number and this graph had been flipped over down here, my range would have been y is less than negative 6.